Good afternoon and welcome to the technical forum of Hydrogen Fuel Cells Europe here at the Hannover Messe 2023. Get comfortable, find a nice seat. We have another interesting topic to discuss, and it's about leak testing. Mr. Sato already just highlighted the devastating effects, potential effects of hydrogen leaking. It goes beyond just environmental impacts, so it's about safety as well. And talking about leak testing, we're going to talk about good practice of leak testing on bipolar plates, and this will be done by Pfeiffer Vacuum. And please welcome to the stage leak detection application engineer, Dr. Rudolf Konwitschny.
Thank you very much for the kind introduction. Ladies and gentlemen, thank you for your time to attend this talk. I'm going to talk about the basics, or basically a fundamental approach on how to start with leak testing. So how do we start? The first approach is ask the experts. So when should a leak test be performed? In principle, leak testing is something which is unwanted. It just costs time, it costs money, and so on, and it does not add value to our product. So when should we do leak testing? One option is, for example, after production of the monoplate. Because if I'm joining two plates and I have one defective plate and one good plate, then I'm losing basically a good part. Also something that I do not want to have. And basically, the pros would be minimum scrap. It's also good to have direct feedback to press operation, so I'm losing comparatively low amount of parts before I can take corrective actions, and I don't need to produce a lot of parts before I notice that something goes wrong. However, again, this is a step which is costing time, money, footprint. Taking a balance on what the pros are and the cons are, in my daily life, I experience comparatively low interest in leak testing monoplates. This is completely different with leak testing of bipolar plates. So after joining the bipolar plates, on the one hand, integrity and also functionality are key issues in order to produce good parts which are functionally tight, which provide the sufficient safety and functionality in long-term operation. Again, it costs cycle time, it costs money, and it costs footprint. Recently, I've come across an approach where a length of almost 50 meters was reserved for leak testing only. So this is quite demanding. And the question is whether we need to do this, whether we have to do it, or whether it goes more cheaper and more effectively. So how should a leak test be performed? There is a brochure from the VDMA, the Association of German Machinery and Plant Manufacturers, in collaboration with one of the leading engineering institutes in Germany, the PEM Institute of the Rheinisch-Westfälische Technische Hochschule in Aachen. And these two groups have joined together and have published a brochure about production of bipolar plate components. There is also a chapter about leak testing, and the schematics is a little bit general. And what they are telling us is that there is a quite narrow range of test pressures which is applied in real-life industry. And also the cycle time range is pretty high. So we are talking about a factor of 3 between 20 and 60 seconds. So imagine that we are targeting cycle times of 1 Hertz, so 1 bipolar plate per second. This means that we need an awful lot of parallel stations or multiple bipolar plates per station. So this is still something that we need to work on. Also, the test sensitivity, the pass-fail criterion, which is in this publication, covers a broad dynamic range, impressive range of 4 decades. So, of course, we must not understand this as a recommendation. It is basically an image of what is out on the market. So there is no common ground, there is no common understanding about the functional leak rate that we need to test for in order to have a long-term operation, reliable operation of a complete fuel cell stack, for example. So all these dynamics, all these parameters are out in the field. There is leak testing with air out in the field. There is leak testing with tracer gases out in the field with quite a broad dynamic range of requested sensitivities. And the tracer gases which are proposed are also air, helium, nitrogen, hydrogen in various dilutions, 100%, 5%. So there is a wild mix of test recipes out in the market. The technology alternative, which are also mentioned in these publications, are, for example, flow measurements. Okay, yes, this is a technology alternative. I do not agree with ultrasonic detection, because if we're looking at detection limit of ultrasonic leak detection, we need a flow that generates sound. And this is only the turbulent flow regime. So we are talking about a sensitivity limit which is higher than the requested one. So we're talking about, let's say, 0.1 millibar liter per second or even higher. So I do not agree that ultrasonic leak detection is a possible technology alternative. Outside-in methods are also mentioned, but as a golden rule of leak detection, you should always simulate the pressure gradient, the force which is applied in real life, also during a test process. So I also would rule out outside-in methods. And what's more, if you're applying outside-in methods, you will have conductance limitations, the flow limitations through the flow field of a bipolar plate, for example. The flow resistance is much more drastic at low pressures compared to high pressures. So that's also one of the technology-related reasons why I would not go for an outside-in method. If we go one step backward, there are existing regulations which are summarizing existing leak test methods, and they are summarized in regulations, for example, European Regulation 1779 and ISO 2485, so worldwide validity, and they are grouped according to various criteria. So on the one hand, the first decision criterion is whether we have an outside-in test or an inside-out test. The second is whether we are going to test integral or localizing. And the third one is whether we are having the full scope of the part to be tested or only a part of it. And there is a broad range of potential methods. We are not going to go through all of them because we can exclude outside-in methods and localizing methods from the beginning. We want to make a quantitative integral test. So we can exclude locating methods and also methods with a flow from outside in. And what is remaining are quantitative methods inside out. But we can also exclude some of them. For example, the bombing test would be for hermetically encapsulated parts. So this is a special version, and some of the other ones are part of other groups. So we can stay with basically 4 fundamental methods that we can apply. Now looking at these tests in more detail, we can characterize them, for example, with respect to the medium that we are using. And of course, accumulation test. Accumulation is basically the collection of escaping tracer gas in an envelope in a test chamber around the unit to be tested, but at atmospheric pressure. So we are making a circulation inside this space, and we are detecting the concentration rise of a tracer gas inside this test chamber. And then we can calculate and track back and use this as a comparatively cheap quantitative method. The vacuum technique is basically also measuring inside out, but in a vacuum chamber. So this, by experience, normally is faster because the gas distribution inside the chamber is faster. And the sensitivity of the method is higher because we are reducing the background of the naturally ambient tracer gases, for example, helium or hydrogen, in air. So in vacuum, we have a reduced background, we have a faster tracer gas distribution inside the test chamber, so that's why this method is faster. Of course, tracer gases are more costly than air, and for that reason, for reasons of initial cost and also for tracer gas costs, running costs, often air is more favorable as a tracer gas. Talking about the detection limit, well, this is a personal analysis from myself. So don't nail me to the cross, the people who are leak testing with air. I'm quite negative about the detection limit of pressure decay methods. For what reason? So let us take an example on how to develop a leak detection specification for a bipolar plate. One of the few data which is available in regulations is coming from this ISO IEC 622 and so on, which is for fuel cell stacks. And often people say, there is a certain value in this regulation and I go down from that. Looking at this specification, looking at this regulation, there is nothing about a pass-fail criterion in the paragraph about leak detection. Only in the paragraph about repeated leak detection, there is some indication that the leakage rate in a repetitive measurement must not deviate by 10% or a value of 5 cubic centimeter per minute, whatever the higher is. So in practice, many people are saying, okay, we have this 5 SCCM. Yeah? They're making the conversion from CCM to SCCM, from a value which is measured with a real test recipe to a value which is standardized. So this is transition which is not taken into account much precisely out in the market. So people are just saying, okay, we have a spec of 5 SCCM, we can convert this now into millibar liter per second, the unit which is typically used in the tracer gas world, and we are down to, let's say, 8.4 times 10 to the minus 2 millibar liter per second for a stack. And then, in this regulation, there is also quite an interesting sentence which says, a stack with a reduced but still representative number of cells may also be used. It is not mentioned what is the minimum number of bipolar plates regarded as representative. So if I want to break down to a specification of a single bipolar plate, I must assume that the amount of one still is representative. Open question. So if I break this down with this amount, I end up with a specification in the lower 10 to the minus 4 millibar liter per second range. The regulation says make a medium conversion from hydrogen to helium. And it also says take a safety factor. Yeah? So this is my personal pain, my personal fear that I'm applying, and then I'm rounding down and I'm achieving a value in the 10 to the minus 5 millibar liter per second range, which is too strict to be handled with pressure decay or any leak testing method with air. This is the tracer gas world. And the question is this the full truth? Not necessarily. So this is a real measurement, a flow measurement of a welding defect. So just a little bit of sparking during a welding process can easily be detected with flow measurement, with air-based measurement. But this is a macroscopic defect that I can see. This is visible. So I'm achieving full range saturation of a 5 SCCM measurement device within a few seconds of time. So I can recognize the signal much faster. So it's a fast method, yes, but not with the required detection limit. So the detection limit of 5 times 10 to the minus 5 would mean a pressure change of 10 Pascal in a measurement time over 60 seconds in a volume of 30 milliliters, which is typically the volume of a bipolar plate plus the pipework in pressure decay systems. But already a temperature change of 0.02 Kelvin will yield the same signal just due to the temperature change. And the bad news is we want to do the leak testing right after a welding process, and we have to pressurize the part, so we are adding compression heat. So obviously, there is a lot of subject for environmental influences in leak testing with air at this sensitivity level. And this is not the case in leak testing with leak testing with tracer gases. Leak testing with tracer gases is more independent of the volume of the respective unit under test. I can measure very large devices as well, large bipolar plates, large devices. Tracer gases are insensitive to volume and temperature changes. They have a pretty good gauge capability, and the bad news is they have the higher investment cost and the higher running cost. So still, for me, the most suitable bipolar plate test method is the vacuum technique. For what reasons? When I started, or in the early days of leak testing bipolar plates on an industrial scale, so only 3 years ago, we had the requirement to do a lot of tests. All potential leak channels in both directions, so inside out, outside in the various flow channels. And also individual channels from the interior to the outside, and also a common summarized gas loss to the outside. This has developed to unidirectional paths, so we are skipping the testing in both ways. And right now, we are in a phase where we have a lot of real test recipes on the market. And what is landing on my desk, the majority is in the 10 to the minus 4 millibar liter per second range, so we are in the tracer gas world. So the next steps would be improve this technique with respect to investment cost and running cost. So possibly make parallel stations, go for cycle time, and this is the most important thing. So this is the highest pressure that I'm experiencing in my daily life, and we are going the step now at Pfeiffer Vacuum away from just supplying instruments to supplying sub-assemblies, which can then be incorporated into production lines. So talk to the experts in leak detection. You do the machinery job. Thank you very much.
Thank you. Thank you. And a warm applause to Dr. Rudolf Konwitschny from Pfeiffer Vacuum.
Thank you very much.